As a company, our mission is to encrypt the web, because our core belief is that the issue isn't that data breaches happen, it's that what does get breached is plain text data. So by encrypting data, it kind of mitigates most of the risks associated with data breaches. And the way we go about doing that is by giving developers really simple tooling and infrastructure that makes it easy to encrypt sensitive data as it enters your infrastructure, and then decrypt it as it leaves your infrastructure on the way to third-party services or to be processed or whatever. And the way we've gone about doing that in the short term is kind of our two, I guess, foundational products, Relay and Cages. Relay is effectively a proxy that encrypts sensitive data as it enters your API, and then decrypts it as you pass it on to third-party services. And then Cages are secure serverless functions for processing encrypted data. And as you can imagine, the kind of volume of the volume and type of sensitive data that's entering these products is something we have to take very seriously as an encryption infrastructure company. Not only is having really robust encryption important, but also having really robust infrastructure is also extremely important as well. So designing kind of everything that we build with that in mind is something that we don't take lightly, and is sort of the foundational basis of this talk as well. But overall, I think everybody kind of understands that crypto is a very dangerous thing. If you go to any forum online, Stock Exchange or any of these online forums, people generally discourage new people from learning crypto who haven't explored it before. There's quite a lot of gatekeeping, and although we obviously want to end that, a lot of the time there are good reasons for that. And overall, we're just trying to keep crypto as isolated and abstracted away from kind of the code that we write day to day. So when we were designing Relay and Cages, we basically had to figure out a way of having a centralized encryption engine, which kind of did all the cryptographic operations. Everything was isolated, and we had a single sort of source of truth for crypto implementations, which meant that we weren't going to have kind of buggy implementations and kind of just a much larger attack surface in terms of the kind of crypto stack itself that we're working on. So as we kind of moved towards that, we ended up designing the Evervault encryption engine, or E3 as we call it. And when we designed it, there was just three very, very simple kind of design principles that we had in mind. The first is that everybody in the Evervault team should not be able to access our users' data. That's an obvious one, but kind of designing with that in mind is tricky. It had to be adaptable for everything that we were going to be building on top of it. So Relay and Cages being the first pieces, but down the line, it's sort of every piece of encryption and tooling, or just generally kind of a platform that developers need to build and process encrypted data overall. And then kind of having a consistent sort of RPC framework for actually communicating with the encryption engine itself. And then thirdly is this sort of magical triad of low latency, high throughput, and complete redundancy, which is, I guess, ultimately the holy grail. But thankfully, over the past few years, these things have become more and more manageable. More practically speaking, what the encryption engine itself had to be able to do was sort of reasonably straightforward cryptographic operations using crypto suites that most companies are using. If you're using TLS today, you're already using elliptic curve Diffie-Hellman and AES 256 for the most part. Shamir secret sharing is a little bit stranger, but the kind of crux of it is that these are all kind of tried and tested crypto suites, and kind of there's nothing particularly novel there, but it all kind of ends up being a major deal in the implementation itself. So this is sort of the software side of things, but like, where do we actually run this thing, and how do we actually run it in a way that means that we can't get access to it and that there's no issues of data leakage? That's where AWS Nitro Enclaves come in. This is a new product that AWS released earlier this year. We were a design partner for it, and it was a very kind of graceful launch. I think for the most part, very few people know about it, and despite it being kind of a core feature of EC2, AWS, for better or for worse, haven't done a great job of actually communicating its value to, I guess, their customers, but also just developers more broadly. But what they are, in a nutshell, is basically in an EC2 instance that you have running, you can carve out resources, create a secondary sort of EC2 instance that can only communicate with the parent over a single AF VSOC socket. I wouldn't expect most people to know this, and if you do, I'm sure you spent too much time for your own good in sort of the underlying Linux kernel and kind of playing with hypervisors and stuff, because the only place that we know of that this is used in production is in virtualization. So if the hypervisors or a parent instance are communicating with VMs, it's a special type of kind of TCP/IP socket. But AWS very both intelligently and kind of painfully decided to build on top of this, and this is the only way that you can actually talk to the enclave itself. Enclaves are basically built from a sort of Docker-esque system where you create a Docker file, you load in kind of statically compiled binaries and kind of everything else that you need. But the kind of most important design principle of Nitro Enclaves is that you basically have no I/O. The only thing you have is access to sort of a CPU and memory. You've no hard drive, you've no network access, and you've no other kind of ways of data leakage, which from a security perspective is great, but from an implementation perspective is not so great. And then finally, it gives you access to what's called the Nitro security module, which actually runs in all of AWS's EC2 boxes. Basically, it gives you kind of direct syscall access to a chip that they've been using to replace their hypervisors. That gives you things like entropy for random number generation in crypto, as well as a feature that they have called attestation, where you can basically prove that what's running inside an enclave is exactly as it's intended to be. It hasn't been tampered with, and so on. But this is all kind of pretty low-level stuff. And I think that the overlap between people who are using AWS Lambda and AWS Nitro Enclaves is pretty small for the most part. Although everyone's using Lambda these days, you're definitely targeted at a different type of developer. This is kind of like just a rough architecture of what we're building and what it actually is designed to do. You'll see that E3 itself is kind of just this really simple strip back system that runs inside an AWS Nitro Enclave, and then everything that we build on top of it just communicates with the E3 enclave itself, which is, for all intents and purposes, effectively baked into the kernel. You have to go through one of these vSock sockets to communicate with it, but it means that we can just sort of abstract it all the way and just build everything on top of it. All the communication happens over message pack, which is I'm sure a lot of you have come across it, but it's effectively a serialization protocol that makes it really easy to serialize JSON to efficient binary byte streams for kind of putting through a socket or anything like that. Because we need to design an RPC framework that had very limited functionality so that we weren't kind of having issues with data leakage and so on. Most of the background that we have as developers and kind of previous work that we've done as a company was mainly focused around Node.js. And I think when you come into a scenario like this where you're dealing with socket types that you've never heard of and so on, it becomes clear that systems or programming languages like Node or Python or Ruby are just fundamentally bad decisions to implement a system like this in for a bunch of reasons. But these four are kind of the main ones that became obvious to us after we started kind of experimenting with how we'd actually deploy this. Garbage collection for most people is totally fine, but for us, assuming that there's a lot of scale going through the whole system, and because we're in the critical path, every single microsecond of latency that we have in our system is another microsecond of latency for kind of our customers, or kind of the users of the developers that are building products on top of Evervault. And that's where things like P99 latency are extremely important, which meant that garbage collection pauses in most of these languages were just painful and something to be avoided. The second is just even the idea of talking about VSOC and Node.js is horrible. I don't even think there's a library out there for it. E3 itself stores a lot of kind of sensitive key material, so we wanted really tight control over how it was accessed, how you can manage it, whether it was sort of belonging to a particular subset of the program itself or anything like that. So tight memory management is also important, which fortunately and unfortunately you don't get in these languages. And then fourthly, you've probably seen a lot of the stuff related to dependency poisoning recently. Every single Node.js project that I've seen has thousands and thousands, or in certain instances, millions of kind of modules that are depended on through kind of a really crazy dependency tree. And if any one of those packages gets poisoned, then you're all of a sudden you're shipping data off to a third party somewhere in some malicious country or some malicious company that you really don't want your data going to. So being able to minimize that is super important. Once we started looking at Rust, these are the main reasons why Rust became kind of an obvious choice for us. The first is sort of no garbage collection. Nitro Enclave itself exposes certain syscalls that you just wouldn't be able to access in a higher level language. And then also we could kind of just communicate directly with the kernel itself without having to deal with message passing between different tech stacks or programs that were running on the same machine. From an IO perspective, Serta is incredible. I'm sure it's sort of like these days it's kind of the hello world of building an internet-enabled application in Rust. Everything that deals with sort of serialization or deserialization uses Serta, and for us, we were kind of no exception. It's excellent. And especially the integration with message pack made things super easy for developers to just send us JSON, we serialize it, send it to E3 and get the response back without having to do much at all. There's a little bit of latency overhead, but it just became clear that this was a good choice. Memory, we just didn't have to worry about this at all. The borrow checker and kind of just having a really tight control over having well-written source code meant that we don't have to worry about sort of malicious pieces of source code within the same project kind of interacting in ways that we don't deeply understand. From a security perspective, this is kind of one of the funny things about most people kind of implementing Rust these days is sometimes you just can't use dependencies because you even get your thing to work in the first place. You have to modify every single dependency you use. I'm sure if any of you have been kind of working on modifying Rust projects recently, putting like a derive clone macro on top of every single function is pretty painful, but I think it has to happen. So we've gotten to a point where we basically have certainly less than 10, maybe less than 5 external dependencies in everything that we build, one of which is the crypto library itself. And then finally, static compilation just makes everything extremely simple and streamlined from a CI/CD perspective. We can just push it to GitHub, it gets compiled in a GitHub action, and then deploying it is just really straightforward. So I think the main part of this talk is just sort of sharing a little bit more about what Rust crypto libraries look like and what the ecosystem in general is like. But when I was sort of scouring the web, both and kind of preparing for this talk, and then also as a team when we were looking at the different crypto libraries, we were expecting there to just be a ton of them. The sad truth is that there's at least three that are production ready, and they all kind of have their quirks to them. The first one that's probably worth running through, and it's the one that we use. This Rust OpenSSL library that's actually a GitHub kind of path. So if you just go to that on GitHub, you'll be able to kind of find the repo directly. But we've all played with OpenSSL before. It supports everything. It's been around forever, and it's just like this like megalithic piece of C code and assembly and everything that no one really understands what's going on there, but everyone trusts it. It gets sort of gets audited all the time. There's bug bounties, not from OpenSSL themselves, but certain companies sponsor them, and it's just it's probably one of the most kind of robust pieces of code on the internet these days. And powers most of the kind of TLS protocols that we're using in web browsers and so on. The downside of Rust OpenSSL is that it's basically not Rust. It's just FFI. You're basically taking the OpenSSL C library, creating a couple of wrappers around them and kind of directly interfacing with it, which is great from a, I guess, safety perspective, and that there's basically no new code. But it means that you're throwing pointers around and you're trying to pass memory between a Rust program, which is theoretically safe, and you're passing it into a C program, which I think, I don't know what the antonym of theoretically safe is, but it's somewhere between theoretically safe and theoretically unsafe. You get very few of the runtime benefits of Rust. Every time you pass a malformed string or malformed piece of data into OpenSSL, you get a panic, and not one of these sort of catchable or unwindable panics, but like a full-on panic. Sometimes you get like a proper seg fault as well. It's not a nice place to be when you've got errors in Rust OpenSSL, but there are ways of kind of catching this and working around it. Something that a lot of people are probably familiar with, even separate to Rust, is compiling OpenSSL is kind of, it's something that at least I've personally lost days of my life to. I think other people are no exception. Like, thankfully these days there's a lot of kind of pre-compiled packages that we can just get from mainstream package managers and so on. But if you're kind of dealing with any of the more esoteric pieces of OpenSSL, you're gonna have to download it and compile it from scratch. And doing that dynamically is painful. But if you've got a Rust binary that needs to be statically compiled, like, good luck. There's a few open source projects out there, but for the most part, it's just basically dominated by a couple of Docker files that you run inside GitHub Actions that sort of solve this for you, but no one really knows what's going on. It's very much a Rube Goldberg machine of kind of the Rust linker and everything just kind of working together and trying to make sense of the whole thing. And then also in Rust OpenSSL, there's a lot of missing functionality. OpenSSL itself has so much stuff, but Rust OpenSSL just hasn't picked up on the majority of it yet. So that's very much still an open problem. The second library is thankfully native Rust. It's a package called Ring. Brian Smith is the guy behind it. And I think when you're kind of looking at Ring itself, in some ways you're looking at the project, but in many ways you're also just looking at Brian Smith and kind of how active he is in both the Rust community and the crypto community. I think overall, the implementations are extremely well thought out, probably to the point of being painful and actually integrating with existing systems. But everything's opinionated. Things like Russells and other kind of mainstream crypto libraries that are used and sort of abstracted in Rust are built on top of Ring, and it's also super fast compared to OpenSSL. There's certain instances where it can be 2 to 3x faster in terms of kind of like the number of operations you can do per second or a similar metric. I alluded to it just there, but one of the major downsides is interoperability. If you've got any kind of crypto system that's in a language other than Rust or in a framework other than Ring, that's another scenario where you're pretty screwed. We lost a couple of days of productivity actually trying to figure out how the Rust library wasn't working with what we built, and it was because basically we misread the difference between SECP 256 OR1 and K1. A lot of the time they're kind of shortened to P256, but in this particular scenario, OR1 kind of dominates most of the time, and or K1 dominates most of the time, and OR1 is just a strange implementation quirk that we picked up on in Ring, but meant we had to abandon the whole thing. The second is also it's extremely difficult if you're new to Rust, even if you're extremely experienced with crypto. It uses closures a lot, and then kind of figuring out how that works from a lifetime perspective is not nice. You get errors that don't really make sense, especially if you're just kind of learning how lifetimes even work in the first place. So it's definitely one probably to follow up on after OpenSSL. Then the final one is Rust Crypto. This is actually a collection of different crates and packages. It's a little bit all over the place, but it is actively maintained. It's all pure Rust. And then they have kind of nice integrations with each other where they all kind of implement common traits that you can kind of you convert different hash types and resulting hashes and kind of rehash them and so on, just with a couple of methods that are just really easy to access on each instance of a Rust Crypto struct. On the downsides, there can also be a lot of inconsistency because they're separate crates. Some are way better than others. Some haven't been touched since they've been developed. Some haven't had security audits, and most of them are pretty hairy around the edges. But it is a nice sort of start in kind of having a unified crypto crate overall. Overall, at least from our perspective, Rust OpenSSL is the clear winner. But this is sort of something that brings a lot of sadness, at least to me personally, because the best crypto library in Rust is actually written in C, which is a pretty unfortunate truth, and I think something that we all could spend a lot of time working on, and hopefully we can solve. But overall, I think we can distill it down to two things that need to happen. And if anybody's both interested in crypto and also interested in Rust, this could be a kind of good place to start. I think that the first piece is reasonably ambitious. It's basically rebuilding OpenSSL from the ground up in Rust. You get all the sort of performance benefits and runtime benefits, but with none of the memory safety issues that OpenSSL has sort of been plagued with for basically since its inception. This one's pretty tricky. And then secondly, just building really nice libraries so that you don't have to worry about what different elliptic curve types are. You just want a function that you put data into, you put a key into, and you get the encrypted data out. This is what 99% of developers need. And I think for us as a company at Evervault, it's something that just became obvious to us as well. But most developers don't want to be handling sort of low-level primitives.